Today's topic is 26.4 radioactive decay. Radioactive decay is a random and spontaneous process. This is a revision for A-level physics. So you must know what is random. A process you cannot predict which particular nucleus is going to decay next. And then usually the examiner will want you to also add in. It is one of constant probability of decay per unit time of a nucleus. And spontaneous decay is one that is unaffected by environment changes, such as temperature or pressure. It means temperature or pressure does not affect the decay rate at all. It will still be the same. Law of radioactive decay. Rate of decay, or the number decaying at any time, is proportional to the number present. So we write it in the equation form. Lambda is a constant, negative, because as time increases, your number decreases. N is a number present at time t. Right? We can rewrite that, take the n down, forget about the negative sign there, then we can give a special name for lambda. Right? dn is a small amount that you measure in a small time interval dt. So dn dt is just your probability or fraction of decay per unit time. Usually the time we take is small. And then this is differential equation. So the solution to this differential equation is n equals to n naught e minus lambda t. N is the number present at time t. N naught is the number present when you start the counting. And it's an exponential decay. Right? It has exponential decay. E minus lambda t. And draw a graph of the exponential decay where this is number and then the x-axis is your time. And that at the end there, where it touches the axis, there is n naught, the number present when the time is 0. Then we can define, if it's exponential decay, we can define the term half-life is the time taken for the isotope to disintegrate to half their initial number. And we can obtain this equation, right, by deriving it. It's given in the data sheet, lambda 0.693 over T half. This is your half-life. Or we can rewrite that, right? Ln n. Ln n is equal to 0.693. And we can define activity is rate of disintegration. Right? Activity, rate of disintegration, or the number disintegrate during that time or interval that we measure. And it's Becquerel, PQ. To remember the scientists who first discovered radioactivity, or we call it counts per second. And then from that equation there, remember activity is a number, doesn't have a sign, negative or positive, just a number. How many per second? We can write as n lambda. And sometimes they may ask you to convert to Curie, and they will give you 1 Curie is 3.70 times 10 to the power 10 becquerel. And there are terms that you need to remember. Fraction remain. You can derive this formula using the half-life. Right? Fraction remaining is n over n naught. N over n naught. Take the n naught. Yeah, cross multiply. You get e minus lambda t. Right? Or it can be 1 over to the power n. N is the number of half-life elapsed. So the time is n times t half. Right? That is the alternative formula. Either this formula, calculate, or this formula. Whichever is easier in the exam. This formula is based on your definition of half-life. Okay, now we can use activity present now. The time t divided by the original activity, that fraction is e minus lambda t. Okay, so that's the exponential decay. Initially, n naught equals to half at one half life. Second half life is half of 0.25, 0.5, 0.25. Another half will be half of that one there. It's just that, right? You should be able to draw that, sketch that graph there. And another half life will be half of that division, and so on. So the number of daughter increases. That's the red one is the daughter. Number of parent, the blue one is the parent, decreases. At half-life, both of them are the same. Number of parent equals number of daughter. And then this curve will run parallel to the time axis after 5 half-life. Right? Approaches closer and closer and becomes 0 at infinity. What is given? This is from a data sheet. Commonly, we will need this value and rest mass of proton and atomic mass unit. Right? And then you will find sometimes you will use K, Boltzmann's constant. And sometimes we will also need to use this one. 1 year is 365 days, 1 day is 24 hours, 1 hour is 3,600 seconds. Formula, there's a formula given. We just convert this one to N, then be N, or this one to A, that will be A. And there's your formula for your relationship between half-life and decay constant. Okay, let's look at 2002 November. Question number 8. Define in term of radioactive, define the term radioactive decay. Quite common. Probability of decay per unit time. That's all you need to write. State the relation between the activity A of the sample of radioactive isotope containing N atoms and the decay constant lambda. It's just memory work. Right? You'll see a lot of questions will use this formula. Radon is a radioactive gas, have a half-life of 56 seconds. For health reason, the maximum permissible level of radon in air in building is set at 1 radon atom for every 1.5 times 10 to the power 21 molecules of air. 1 mole of air in the building is contained in 0.024 meter cube. Okay, so 1 mole, that's the volume, that's 1 mole of air. So they wanted the number of molecules of air in 1 meter cube. You have to go to your data sheet. Right? That is what the volume. That's the number of molecules, Avogadro's number in that volume of air. So 1 cm cube, 1 meter cube, you just divide this by 1 meter, divide this by 1 meter, then you get divide this by 0.24, you get 1 meter, divide 0.24, I get 1 meter. You get the number of molecules present in 1 meter cube. Okay, so that's what we have calculated. The number of air molecules present in 1 meter cube. Maximum permissible number of radon atoms in 1 meter cube. Okay, is given us 1 radon in 1.5 times 10 to the power 21 molecules. So I have this number of molecules and 1 radon in these molecules. So we just divide. Right? Number of radon atoms to be this number divided by this number. That's what we get. 1.60 and 10 to the power 4. Maximum permissible activity of radon per meter cube. Half-life is given. Right? They are asked you to the relationship earlier. A equals to n lambda. So now they will be using it. So from half-life, right, from your data sheet, we calculate a lambda 0.693 as your half-life, 56. 50 is in second, this will be per second. And the relationship A activity is n lambda. So n is just that times your lambda. That's why we get 210 becquerel or counts per second. Okay, this is supposed to be in AS, but it has changed to A2 since 2016. A student is provided with a freshly prepared sample of radioactive material, and the count rate from the source is found to vary with time as shown in figure 6.1a. That's one. The second similar sample of radioactive material is then prepared, and the student repeats the experiment but the sample at a higher temperature. The variation with time of the count rate of the second sample is shown. So this is for the second sample where you have at a higher temperature. Sure, the same thing. State evidence that is provided by these two experiments for the random nature of radioactive decay. If it's random, you can just go this way and go that way and go that way. But when you detect your radioactive source, this one is your radioactive source, your detector will be there. So sometimes you throw out more here. Sometimes you throw out, there's your radioactive source, there's your detector. The detector is only one side. Sometimes you throw more out here, sometimes throw more out that way, sometimes throw more out that way, sometimes throw that way. Right? So that's why it's called random, no fixed direction. You can do it throughout the particle any direction. So we can see that from it's not a smooth curve, sometimes more on one side, right? Sometimes less on one side. Right? So it's not smooth, or we call it fluctuating. Spontaneous decay. Right? Remember we say spontaneous, it doesn't depend on temperature. The shape is almost the same. It means the half-life is the same, or the exponential decay is the same. Right? Curve, same shape, or same half-life, showing not affected by temperature. Okay, sometimes they may ask you to draw, right? They say isotope magnesium 56 decay and undergo beta particle emission to form the stable isotope iron 56. Half-life is 2.6 hours. Initially, at time t equals 0, the sample magnesium 56 has a mass of 1.4 microgram, and there's no iron. On figure 7.1 shows a variation with time of the mass of iron in the sample for time t equals 0 to 11 hours. So they want you to sketch for until 11 hours there. Okay, so to sketch, we just use the definition for half-life. If you initially start with that, of course, choosing the right scale, right? They intentionally give you a good graph. If you choose the right scale, then it's easy to draw, to sketch. Okay, so first of all, first half-life is 2.6, right? They are given you 2.6. Second half-life, 5.2. Third half-life, just times 3 there, get 7.8. And you just add these two together. Fourth half-life, 3 and 1, you get 10.4. Okay, and then choose a proper scale. Start with this one because there are 7 divisions here. So 1.4, so each division is 0.2. Right, you can write a scale there, and it will help you. And you start with initially at time t equals 0, 1.4, and after one half-life, 2.6, 3 is here, 2.6 is around there, or nearly 3 there, is 0.75. Okay, and after another half-life, which is 5.2, about 5 is there, 5 is there. Half of this one is 0.375. So put another cross there. And another half-life is 7.8. 7 is here, 10.8 is nearly 8 there. Right? So half of this one is 0.19. Just draw that, or nearly 2 there, 0.2 there, nearly there. And then another half, 10.4 is half, just roughly estimate half of this one is around here. Let's sketch your graph. Okay. If you are asked to sketch the daughter, remember, will start from 0, and then first half life will be here. After one half life, it will be here, increase to half the number. And after another half life, right? This is 2 division from the bottom. So this is about 2 division from the top there. Same thing, right? That amount, that distance from the bottom, that distance from the top, and so on. You can sketch. All right. So that's your iron. It's increasing. For manganese 56, determine the initial number of manganese 56 atom in the sample. Okay. So you need to know what is given. Half-life is given, 2.6 hours. Initial mass is given, 1.4 microgram. So use Avogadro's number. Go to data sheet. Avogadro's number. Right, from here, 56 gram contains 6.02 times 10 to the power 23 atoms. So if it's 1 gram, then you divide this one by 56. 56 for 1 gram. Then for 1.4 microgram, you times 1.4. Remember, this is micro, so to times 10 to the power minus 6, change it to SI unit, gram, in gram. And our answer is in gram. Sorry, number of atoms. Right? This must be in gram, because this one is in gram. Okay, so we calculate the number of atoms, manganese atom, initially. Then the other formula you need to recall. That's your N. So A, first of all, you haven't got your lambda first. You have half-life, so you can calculate your lambda, your decay constant. Your data sheet, this formula, you can remember so much better. Ln 2.6 times 3600. Right? 1 hour equals to 3,600 seconds. Calculate out. Either leave it per second, or if you don't divide by 3,600, then you get 2.267 per hour. Right? So either answer can be okay. And remember the activity formula, n lambda. This is your n. This is your lambda. Right? If you run it per second, so that is your background per second, hours per second. The one in your answer should be per hour, hours per hour. Okay, you want to determine the time where the ratio of mass of iron to mass of manganese is 9. Okay? The time where iron has increased, manganese has decreased to 9 times that of manganese. Right? We can rewrite that. Right? Iron, let the mass be Fe, manganese, Mf, Mn. Right? And then you just cross, this is equals to 9. You take the manganese across there, you get 9 there. And the total present initially. Remember, the iron came from manganese. So as the manganese decreased, the iron will increase. So the total mass initially will be the amount of iron present at this particular time plus the manganese present at this particular time. And then we know iron in terms of manganese, you add 9 plus one of them is 10 mass of manganese. Right? So fraction of mass remaining, mass of manganese present is just that one there. And then initially it's just 10. So you get 0.1. 0.1 fraction left. Then activity, fraction left is A over A naught, E minus lambda T. Right? Take ln of that, we got your minus lambda T. So put in all the things that we have calculated, lambda we have calculated there, the second or per hour. Right? Since it's going to be a large value, you might as well calculate per hour. Okay, so ln 0.1, 0.267, I'm using per hour, so my answer in time will be per hour, 8.6 hour. Okay, let's go to the next question, 17. Uranium-234 is radioactive and emits alpha particle at what appears to be constant rate. Sample of uranium-234 or mass 2.65 microgram is found to have an activity of 604 becquerel. Calculate for the sample of uranium-234 number of nuclei. Okay, so as before, this is in terms of gram, number of gram for 1 mole. Go to your data sheet, find your Avogadro's number, 234 gram, contain that number of atoms. So we want 2.6 microgram. So therefore 2.65 microgram contains, right? You divide this number by 234 and then you multiply by that one there, 2.65. But remember to change it to gram. This is in gram, so that must be in gram. Use your calculator to calculate the value, the number present. Okay, so the number present, the activity they have given you. So they want you to use the formula, calculate that's your n, a lambda n, put in your value in 604, and that value inside for n, you can calculate your lambda. Okay. Half-life, right? They have given lambda. So basically, they are just trying to get you to remember or how to use a half-life formula. Right? Half-life can get from data sheet and put in your lambda value and then calculate. Right? Half-life is in second. Suggest why the activity of uranium-234 appears to be constant. I can see the half-life for uranium-234 is very long. So very long, it means that it will take a very long time for one to decay. So it means that the activity more or less will be constant. Usually we take a short time, probably 10 minutes or 5 minutes, depending on the activity. If the activity is high, we just take 1 minute to measure. So 1 minute compared to that 10 to the power 12 seconds is very small. So they hardly change at all. Okay, so if you want to convert to years, you can convert to years. Divide by 365. That's a day. 1 day is 24 hours. 1 hour is 3,600 seconds. You can convert to years if you want to. Since they ask you, sorry, you have no choice. They ask you to convert to years, you convert to years. Okay, so in this case, half-life is very long compared with the counting. So it hardly changed. Suggest why the measurement of mass and activity of radioisotope is not an accurate means of determining the half-life if the half-life is approximately 1 hour. This is a short half-life. So during the time that we measure the half-life or the activity, the number will start decreasing. Not like long half-life. Long half-life, it apparently doesn't change a lot. It's almost always the same value. But not for 1 hour. It will start to decrease. Okay? There will be appreciable decay of source during the taking of the measurement. Okay? Sources of alpha particles are frequently found to contain traces of helium gas. A radioactive source emits alpha particle at constant rate, 3.0 65 times 10 to the power 6 per second. The alpha particles are collected for a period of 40 days. Each alpha becomes helium atom. Right? So basically the alpha, it came out of your radioactive source, and then after a while it will get an atom from the air and becomes helium atom. Right? So we are collecting helium gas. By reference, the half-life of a source suggests why it may be assumed that the rate of emission of alpha particle is constant. Right? As always the case. So this is a long half-life. Right? Our timing usually is very short, either 5 seconds. Since this is a large activity, usually we don't need so long. 1 minute will be sufficient. Right? A minute to measure the activity was sufficient. So during that short interval, compared to these 40 days, the activity doesn't change. Right? After the half-life of the source is very long, compared to time of measurement of activity, or the decay is very small. Thus the emission is constant. Either one. Okay, said count rate is very high. Usually we use a short time interval to measure the number present, number emitted. The helium gas may be assumed to be ideal gas. The alpha particle now becomes ideal gas. So it's a good question because now they are testing you ideal gas. Calculate the volume of gas that is collected at a pressure of 1.5 times 10 to the power 5 Pascal and at a temperature of 17 degrees Celsius. Okay, you probably have to start remembering to change that to second. Right? So recall 1 year is 365 days, 1 day 24 hours, 1 hour is 3,600 seconds. Then remember to convert that to Kelvin. 273 plus 17 is 290. And go to your formula. Right? Activity, number collected in the time interval delta t. You just divide number collected divided by the time you make the collection, right? Or the rate of disintegration. Right? Take your delta t across, you got activity times delta t. So that is your activity. Okay, you are told you collect it for 40 days. 40 days, that's your 40 days times 24 hours. 1 day is 24 hours, and 1 hour is 3,600, right? So this is in second, that is per second. So you can calculate your number of atoms. Okay, then we are going to ideal gas. You have to remember this formula. Choose a formula that's best to use. That's your pressure, that's your volume, that's number of atoms, that's your Boltzmann's constant, can get from data sheet, that's your absolute temperature. Put in your value, right? Pressure, that's your pressure, and volume is what we want to find. That's your volume of gas, and we have calculated, that's your N. Then Boltzmann constant get from data sheet, the temperature, just tap on that, and use your calculator to calculate your volume. Okay. Thank you. We have finished that today. If you want some of these resources, you can either go to my Facebook, right? That one you can find the notes and the PowerPoint and the video. Whereas this one, past year paper A2, you can get a topic by topic to practice. You can download the question. The video will also be there. Or you can go to YouTube, search under my name, and you will find A-level revision, radioactivity. Okay, thank you. we will end the lesson since we have completed